In this lesson, we will present the idea of cyclic groups. In a cyclic group, every element can be written as an integer power of a specific element called the generator of that group. Let's be more precise with our definition. A group G is cyclic if there's an element A in G such that G is made up of all integer powers of A. So G equals the set of elements A to the n, where n is any integer. So if G is cyclic, we say that A is a generator of G. And the notation is G is the cyclic group generated by A, so we use these angle brackets around A, the generator. And again, we say A is a generator of G. So this is the notation for any cyclic group. You can write it as angle bracket with just one element inside if that one element generates the group G. First, let's give some notes about cyclic groups. First, any cyclic group could have more than one generator. Since notice that if A is a generator, then the cyclic group generated by A, by definition, is a set of all integer powers of A. But if A is a generator, then A inverse is also a generator. And we see this because as n varies over all integers, the powers of A inverse also range over all integers. So these sets are the same, and we see that if A is a generator, then A inverse is also a generator of this cyclic group. Now if it happens that the generator is its own inverse, then it might still only have one generator. But in a general cyclic group might have more than one generator. Second note, consider the following exponent rules. We see that A to the power n times A to the power m will just equal A to the power n plus m. But then I can write this as also equal to the product A to the power m times A to the power n. So therefore, every cyclic group is abelian. So powers of A commute with powers of A. Thirdly, while we write this set generated by A as all integer powers of A, it could turn out that this is actually a finite set. So if you list out all the powers of A, you might have an infinite number of numbers in your list, but if A has finite order, these powers of A will start repeating. So it could happen that this set may have only finitely many elements. So if A is finite, has finite order, then this set actually has the same number of elements as the order of A. Let's look at an example of a cyclic group. So kind of the quintessential cyclic group is the set of integers. So when we have an arbitrary group, we write the operation as multiplication, but the integers is a cyclic group under addition, and the generator is the integer 1. So I can write the integers as the set generated by 1, and we're not going to write this multiplicatively, we'll write this additively as a set of all multiples of 1. So this would be n times 1 such that n is an integer. So every integer can be uniquely written as an integer times 1. Note that we could also write the integers as the set generated by negative 1. Because we can write any integer uniquely as a multiple of negative 1. So given any integer x, we can write x as negative x times negative 1 for all integers x. So the integers actually has two generators, 1 and negative 1. Let's look at another example of a cyclic group. Now consider the group D2n. Well, we just said that every cyclic group is abelian, so D2n, since D2n is not abelian, D2n is not a cyclic group, but it does have a cyclic subgroup. So the subgroup, let's call it H, of all rotations this is actually a cyclic group. Is a cyclic subgroup with generator R. So let's note this as R with angle brackets. So this would be the identity rotation R squared all the way up to R to the power n minus 1. So every one of these powers of R is a rotation, and this set actually forms a cyclic subgroup of D2n. Next, we'll prove some properties of all cyclic groups. So in this theorem, let's let G be a cyclic group generated by A. So let G be the cyclic group generated by A. Then the order of this group equals the order of the element A. Further, we have these following two conditions. One, if this group has a finite order n, then the group equals the set 1a squared up to a to the n minus 1. If this group has infinite order, then the power a to the m does not equal a to the n for all integers m and n which are not equal. So let's begin the proof. Suppose a has finite order n. Then the elements 1, a squared, up to a to the n minus 1 are all distinct. Since if you had two of these powers equal to each other, so for example, if a to the power I is equal to a to the power j, for some integers I and j less than n, let's see, for some integers I and j, I greater than or equal to 0 and less than j, and j less than n. So if a to the I equals a to the j, then a to the power j minus I would equal a to the power 0, which is the identity element. But this would contradict the fact that a has order n. So we see that the list 1, a squared, all the way up to a to the n minus 1 are all distinct elements. And so we see that the set containing these elements, 1, a squared, up to a to the n minus 1, this is a subset of the cyclic group of order a, because that contains all powers of a. Now we need to show the reverse containment. So now let a to the power k be an arbitrary element of the cyclic group of order a. Then by the division algorithm, we can find integers q and r such that k equals qn plus r, and r has to be greater than or equal to 0 and strictly less than n. So I can write a to the power k as a to the power qn plus r, and then by properties of exponents, this equals a to the n raised to the power q times a to the r. But a to the n is the identity element because a has order n. So this is 1 to the power q times a to the r, which just equals a to the r. So we see that we can write any power of a, so a to the k, as one of the elements of the set 1, a squared, up to a to the power n. Just a to the power k is an element of the set 1, a squared, up to a to the power n minus 1. And since an arbitrary element of the cyclic group generated by A is in this set, we've just shown that these two sets are actually equal. And that we've just shown that the cyclic group generated by A actually equals the set 1a squared up to a to the n minus 1 when A has order n. And we see that the order of the cyclic group equals n, which is the order of A. So this proves part 1 of the theorem. For the second part, let's suppose that A has infinite order. And by definition of infinite order, A to the power n cannot equal the identity, element 1, for any non-zero integer n. Then if A to the power I equals A to the power j, then that's true if and only if A to the power j minus I equals the identity. The only way this could be true is if j minus I is equal to 0, and this is only true if j equals I. Therefore, if you take different powers, if j does not equal I, then a to the I will not equal a to the j. So thus, distinct powers of A are distinct elements of the cyclic group generated by A. Well, so for every integer power, you get a distinct element of the cyclic group. It must be that the cyclic group generated by A is infinite as well. And this finishes the theorem. Now let's prove a corollary. Let A be an element of group G. And if A to the power m equals the identity, then the order of A divides m. So for the proof, let's suppose the order of A is n, and suppose A to the power m equals the identity. Well, if m equals 0, then clearly n divides m. So let's assume that m is non-zero. Then just like we did in the previous theorem, we can write m as q times n plus r for some integers q and r, with r greater than or equal to 0 and strictly less than n. And we saw that a to the power m will just reduce down to a to the power r. Thus a to the power r equals 1, and since the order of a is n and r is strictly less than n, we must have r equal to 0. Well, if r equals 0, then we see that m equals q times n, and therefore n divides m. I finished this proof. Next, we'll prove that any two cyclic groups that have the same order must be isomorphic. So any two cyclic groups of the same order are isomorphic. Let's start off with two cyclic groups. Suppose the group generated by A and the cyclic group generated by B both have finite order n. Let's define a map that will be our isomorphism, showing that these two groups are isomorphic. So let's define our map. Phi from the cyclic group generated by A to the cyclic group generated by B by phi of A to the power k. So if you have an integer power of A, we're going to map A to the power k to B to the power k. Let's show that this map is an isomorphism. First, we'll show that phi is well defined. Suppose a to the power r equals a to the power s, we need to show that phi of a to the r equals phi of a to the s. Well, if a to the r equals a to the s, then a to the r minus s equals the identity, and by the previous corollary, the order of A must divide R minus S. Then I can write R minus S as an integer multiple of n for some integer t, and I can write R as n times t plus s. So if I take phi of a to the power r, that's the same as phi of a to the power n t plus s. By definition, this maps to b to the power n t plus s. I can write this as b to the power n raised to the power t times b to the power s. But b has order n, so this just equals the identity to the power t times b to the power s, which equals b to the s, and that is equal to phi of a to the s. So if a to the r equals a to the s, then phi of a to the r is equal to phi of a to the s. So phi is well defined. Now that phi is well defined, we need to show that phi is actually a homomorphism. If I start off with phi of a to the r, a to the s, that's the same as phi of a to the power r plus s, which by definition equals b to the power r plus s. Then again, I can write this as b to the r times b to the s, and that equals phi of a to the r times phi of a to the s. Thus phi is a homomorphism. Now to show it's an isomorphism, we need to show it's onto and one-to-one. First, let's show that phi is onto. Well, take any element of the cyclic group generated by B, so let b to the power k be an element of the cyclic group generated by B, then phi maps a to the power k to b to the power k. So therefore phi is onto. Fourth, let's show that phi is one-to-one. Well, since the cyclic group generated by A and B are both finite sets, and phi maps the cyclic group generated by A onto the cyclic group generated by B, but these groups have the same number of elements, these sets have the same number of elements, phi must be one-to-one. So thus phi is an isomorphism. And these two cyclic groups are isomorphic. So that finishes the case when two cyclic groups are finite. Next we'll show that any infinite cyclic group is actually isomorphic to the set of integers. So now suppose the cyclic group generated by A is an infinite cyclic group. So we claim that this group is actually isomorphic to the integers via the isomorphism phi defined by phi of the integer k equals a to the power k. It is an isomorphism. First, note that phi is well defined Since when we take an input is an integer, and there's no ambiguity about the representation of integers. So phi is well defined since there's no ambiguity in the representation of the integers. Secondly, this map is actually a homomorphism. So if we take integers k and j, then phi of k plus j equals a to the power k plus j. I can break this up as a to the power k times a to the power j, and that equals phi of k times phi of j. This phi is a homomorphism. It remains to show that phi is onto and one-to-one. Well, let a to the power k be an arbitrary element of the cyclic group generated by A. Then phi of the integer k equals a to the k. So phi is onto. Finally, phi is one-to-one, since we saw that distinct powers of A are distinct elements. So a to the m does not equal a to the n for all m not equal to n in the integers. So therefore phi is one-to-one. So thus phi is an isomorphism, and the infinite cyclic group generated by A is isomorphic to the integers. So we see that the integers is the unique cyclic group up to isomorphism of infinite order. Let's discuss a few points about cyclic groups. So we saw that each pair of cyclic groups of the same order are actually isomorphic, and there's really up to isomorphism only one infinite cyclic group. So the integers is the prototypical infinite cyclic group. So for an arbitrary cyclic group, we want to write it multiplicatively. So for each positive integer n, we'll denote the cyclic group of order n as Zn. So let Z sub n be the cyclic group of order n. I'm going to write this multiplicatively. So up to isomorphism, there's really only one cyclic group of order n. So we'll write the cyclic group of order n multiplicatively as the set containing elements 1 and powers of a generator a. So 1a squared up to a to the n minus 1. And we notice that if we multiply two elements of Zn, we're really just adding the exponents, and then we're going to reduce mod n. So we see that multiplication in Zn is essentially done by adding exponents and then reducing mod n. So although we write a generic cyclic group of order n multiplicatively, by this description we see that the following note, that the cyclic group of order n is actually isomorphic to the set of integers mod n. So z over nz. And originally when we introduced this set, we wrote each element as its equivalence class. So 0 as the equivalence class of 0. These would be all the multiples of n. The equivalent class of 1 would be the set of integers that are 1 more than a multiple of n. But this notation is a little bit unwieldy, so we'll just write this as the set 0, 1, 2, all the way up to n minus 1, where it's understood that each element of this set is actually an equivalence class of integers. And this group has operation addition, and we reduce mod n. So these are the prototypical finite cyclic groups. We can write them as Zn and write them multiplicatively, or if we choose to write it as an additive group, the integers mod n is the prototypical cyclic group of order n.